Hi, I'm Norman Wildberger. We have just started a new series on hyperbolic geometry where I'm introducing a new and far improved way of thinking about this subject. My point of view is that hyperbolic geometry is really the study of a circle, the simplest of all geometrical objects next to the straight line, and that its origins really go back to the ancient Greeks. Hyperbolic geometry could have been developed by any mathematician in the last 2,000 years who knew a little bit about projective geometry and had an interest in Apollonius's work on the circle and conics. So we've been talking about Apollonius's insights into polarity. And let me remind you what we talked about. We're starting with a base circle. And that circle allows us to define the polar of any point. And the first initial naive definition was to assume that the point A was outside and then to look at the two tangents to the circle, and where those two tangents met the circle, we draw a new line. We call that the polar of the point A. But then we saw that there was a more sophisticated and more flexible and better way of thinking about what the polar was that involved two arbitrary lines through A that meet the circle in 4 points. Now those 4 points form a quadrangle, and that quadrangle has altogether 4 other lines through it, meeting at 2 new diagonal points, and it's those 2 diagonal points that determine the polar line. And there's a remarkable fact that underlies this. The fact is that the construction is independent of the choice of 2 lines that we started with emanating from A. So if we change these 2 lines to some other lines, the quadrangle would be different, but the polar line that we get would be the same. We call that the polar independence theorem. And our notation is that capital A is the polar of little a, and we write A equals A perp. Conversely, A is the pole of the line, and we write little a is equal to big A perp. And here we see that we can also reverse the situation. If we start with a line A and we want to know where is its pole, what we can do is we can use the polar duality theorem, which tells us that if B is any point on the line big A, then the polar of B must go through the pole of A. So wherever this point A is, it's got to lie on the polar of B. So if we choose another point, say C on A, then its polar, right here, will pass through A as well. So we can get A by choosing any 2 points on the line big A, finding their polars here and here, and finding where they meet. As a consequence of that, if we think about varying the point on the line A, then its polar will vary through all the lines through the pole A of A. Now, Apollonius realized that that entire discussion actually works not just for a circle, but for a general conic. So we could have just as well started out with an ellipse. This is my picture of an ellipse. Not too good, but not too bad. And we could have done exactly the same thing to, for example, associate to this point, little a, its polar, capital A. Or to associate to this point, C, its polar, capital C. Or to associate to this point, B, its polar, capital B. So these 3 important theorems that we mentioned, the polar independence theorem, the polar duality theorem, and the pole of a line theorem, they hold for general conics. And here are some pictures of that a little bit more accurately with geometers' sketchpad, illustrating, first of all, the story for an ellipse and the construction for a hyperbola. One of the main themes for us as we carry on this course is that when we're studying the plane, the hyperbolic plane, from this point of view of having this distinguished circle that we're starting with and that everything is built from, that the points on the circle actually play a very distinguished role. And we must be conscious of the fact that we have to treat the points on the circle specially. They are different from all the other points. So I recall that our notation for a point on the circle is that it's a null point. We sometimes call the circle the null circle. And we usually use Greek letters to denote points on the circle, or null points. So here's a question that we haven't quite addressed yet. How do we find the polar of a null point, gamma? Such a point also has a polar line, but the prescription that we described up till now doesn't actually work for that. If you try what we were talking about before and you draw two lines through gamma, then you don't get a quadrangle, you get a kind of degenerate quadrangle or a triangle. And that's not enough to construct the diagonals and therefore the polar line. Well, one way might be to think of this case as a limiting case where you have some point outside approaching here or some point inside approaching there. That certainly suggests, when you look at it, that the polar ought to be the tangent to the circle at that point. And we can actually find that tangent in another way by using the polar duality theorem. So what we do is we look at two lines that go through gamma, let's say big A and big B, and we find their poles. So there's the pole little b of this line big B, and there's the pole little a of this line big A. And now what we do is we join little a and little b, and that's going to be the polar of gamma. And it does turn out to be a tangent to the circle. So here's a good exercise for you. Construct a tangent to a null point using this technique. So start out with a circle, draw a point on the circle, and ask yourself, okay, now I'm going to figure out how to construct this tangent by actually first constructing the pole of some line through there, the pole of another line through there, and then joining them up. But each one of those constructions itself will require some understanding of the pole-polar situation. That shows, by the way, an interesting fact. The interesting fact is that we can construct the tangent to a circle through a point on it simply by a straight edge construction. So without using a compass, if we're given a single circle and a point on it, we can construct the tangent. Here's another exercise. It's a starred exercise. And it is, how does one construct the center of a circle using only a straight edge? This is an interesting question because sometimes we don't know where the center of a circle is. For example, when I draw these circles here, I usually use this plate here and I just draw around the plate. So after I've done that, I actually don't know where the center is. You can eyeball it, of course, and say, well, it's roughly there, but that's probably not exactly accurate. So it's an interesting question. Can we theoretically find the center of a circle using only a straight edge? We know that we can find a tangent to any point from the previous page, but then the question is, can we find a perpendicular to that tangent, or maybe some other method? That's a good question to think about, and it's a starred question. All right, now we're going to come to another one of Apollonius's great insights. That once we have our circle and the polar of a point A, right there, then there's a very interesting relationship made by the 4 points of any line going through A. So if we choose any line through A, then it meets the circle in 2 points B and D, and it meets the polar line in a point C. So these 4 points now, A, B, C, and D, have an interesting relation. We say that they are a harmonic range of points. And what does that mean? So if you look at BD and think of that as an interval, then this point C, in this case, might divide it into roughly the ratio 1 to 2, or maybe 1 to 2.5. And the claim is that this point also divides this segment externally in that ratio. So if we look at the ratio of this to this, that's also in the ratio of 1 to 2.5. And that works not just for those 4 points, but also for those 4 points, or those 4 points, or any 4 points formed by a line through A that meets the circle in 2 points. And the notion of harmonic conjugates is saying that A and C are harmonic conjugates with respect to B and D. So when A and C divide B, D internally and externally in the same ratios, we say that they're harmonic conjugates with respect to B and D. As we develop hyperbolic geometry in this course, it's going to be useful to us to keep in mind that geometry comes in different subjects. That not only is there Euclidean geometry, but there are also related but different geometries called affine geometry and projective geometry, and some others too. In fact, there's a kind of a hierarchy of geometries that are determined by their simplicity or by the sophistication of the tools that are allowed in that geometry. So it turns out that this notion of a harmonic range belongs to affine geometry, and remarkably, even to projective geometry. Now those are terms that are going to be important for us, and let's just very quickly introduce them here. So projective geometry is roughly the geometry that you can get in the plane by only having a straight edge. That's the only tool that you have at your disposal. You don't have a ruler, just a straight edge. And you don't have a compass, so you don't have a notion of parallelism, you don't have a notion of perpendicularity, you can't draw circles. The only thing you can do is draw lines through 2 points, or if you have 2 lines, you can find their point of intersection. That's going to in fact be the most fundamental geometry for us. Hyperbolic geometry is really projective geometry with a distinguished circle. That's going to be a main theme for us. But there's a related geometry called affine geometry, which is almost the same seemingly, but still quite different. It's what you get when you have a straight edge, but you also have the notion of parallel lines. So given one line like this and some other point, you allow yourself to know what parallel line means and how to construct a parallel line. Euclidean geometry, which is the more familiar one, has not only a straight edge, but also the compass, and with all the constructions that the ancient Greeks did with those 2 things. Now with the compass, you can not only get parallel lines, but you can also construct perpendicular lines. So that's a way that Euclidean geometry differs from affine geometry. In Euclidean geometry, you have perpendicular lines. In affine geometry, you don't. You only have parallel lines. Now there's actually another geometry that really ought to squeeze in here, which is almost rarely ever discussed, and I'd like to call it carpenter's geometry, where it's the geometry that you get by having a straight edge plus a carpenter's square. Well, actually a carpenter's square already has a straight edge in it, so really it's just the geometry formed by a carpenter's square. And the crucial thing about a carpenter's square is that you can create perpendicularity there with this T-junction, this intersection of these 2 perpendicular lines. So with the notion of perpendicular line, you can get the notion of a parallel line. So Carpenter's geometry is more powerful than affine geometry. Euclidean geometry is more powerful than Carpenter's geometry. So there's really a sort of a hierarchy of geometries here. And whenever we have a concept in geometry, we like to say, well, where does it actually fit in this hierarchy? And somehow, the earlier on the concept fits, the more fundamental it is. So the concept of polarity of a conic actually is a concept in projective geometry. That's why it's very important. And this notion of harmonic conjugates or harmonic range is also ultimately in projective geometry. Even though the way we've defined it, it actually appears to be in affine geometry. It's a very profound fact that it actually is really living in projective geometry, this notion of a harmonic range of points. So let me explain a little bit more precisely, what do we mean by a harmonic range of points, or what do we mean by harmonic conjugates? Here we have 4 points on a line, A, B, C, D, and these 4 points do form a harmonic range. Or to put it another way, A and C are harmonic conjugates with respect to BD, and we'll see that conversely, BD are harmonic conjugates with respect to AC. So let me explain what those things mean. First of all, in affine geometry, we may construct a scale on any line. If you have the notion of parallel lines, then it's possible to repeat a segment on any given line. So if you mark this point 0 and you mark this point 1, then only using parallel lines you can create another marker 2 and then another marker 3 and so on, so that these are all equally spaced. And you can do that using only parallel lines. So in affine geometry you are able to make a scale like this on any given line. However, it's important to make very clear that although you can make a scale on this line and then you can make another scale on this line, in affine geometry you have no way of comparing your unit on this scale, on this line, to the unit on this line. So you have no way of saying that this segment here is congruent to this segment on a line that's in a different direction. But nevertheless, on any one given line we can draw a scale, and so let's assume that we have a scale on our line. And now let's look at the relationship between these 4 points A, B, C, and D. We're going to think in terms of displacements. So our scale is not measuring distance, it's measuring relative position or displacements on this line. So from B to A is a displacement of 6, while from A to B is a displacement of -6, because we're going in the opposite direction. So we can really talk about vectors. We can think of the vector AB, the vector BC, and the vector CB in different directions and so on. Now what's happening with these 4 points here is that the ratio of the vector AB, this displacement, to the vector AD, which is this displacement, is, well, that's -6 to -12. That's in the ratio 1 to 2. While the ratio between the displacement from C to B and from C to D is the ratio between +2 and -4, which is -1/2. So the two ratios AB to AD and CB to CD are equal except for the minus sign. And the minus sign is happening because A is outside the interval BD, while C is inside the interval. So this is the situation of harmonic range or harmonic conjugates, that this ratio and this ratio are equal up to a minus sign. So we say that A and C are harmonic conjugates with respect to B and D. Or, equivalently, we say that the 4 points A, B, C, D, in that order, is a harmonic range. So here's that harmonic condition, that AB to AD equals minus CB to CD. Where here I've got the points on the line going this way, but it doesn't make any difference. And where these quantities here are really displacements, we are not measuring distances. It's an important mistake that is found in many textbooks. Okay? It's not distances. Distances are not at all in the picture here. We're simply talking about displacements on a linear scale created using affine geometry. Okay, so the first thing to observe is that this fact that this ratio is the same as this ratio, up to that minus sign, that it's independent of the choice of scale. In other words, if someone comes along and marks out a uniform scale on the same line in a different fashion, in other words, with a different sized unit, then they're going to measure this separation differently, but the ratio of this thing to this thing is going to be the same as what you've got. So this condition is independent of the choice of scale. Another interesting observation is that we can rewrite this by essentially bringing the CB that's in the numerator here to the denominator here, and bringing the AD, which is in the denominator here, up to the numerator there. Okay, I'm going to do that, but I'm also going to switch some orientations on our displacements, because I want to write it in this way, as BA over BC equals minus DA over DC. So when I replace AB with BA, I'm introducing a minus sign. And when I'm replacing CB with BC, I'm also introducing a minus sign, so they kind of cancel out. And I'm replacing AD with DA, that introduces a minus sign, and CD with DC, that's another minus sign. So again, those minus signs cancel out, and we still have the same minus sign that we started with. So this is a valid rewriting of this. But now we see that this has exactly the same form as this, but with the roles of B and D and A and C interchanged. So it means that AC are harmonic conjugates with respect to BD, precisely when B and D are harmonic conjugates with respect to AC. So going back up to our picture, if C divides BD in the same ratio as A divides BD, one internally and one externally, then also B divides AC in the same ratio as D divides AC, externally and internally. So this notion of harmonic conjugates is symmetrical with respect to this pair and this pair. We don't have to say which one is which. We just have one pair of points, we have another pair of points, we say that this pair of points is harmonically conjugate with respect to this pair of points, or that this pair of points is harmonically conjugate with respect to this pair of points. So it's good to have some intuitive feel about harmonic range of points. So if you see 4 points on a line anytime, first question you should ask yourself is that a harmonic range of points? Okay, so what do harmonic range of points look like? Well, there's a lot of different examples, but here are a few of them kind of illustrate some of them. So I've got a few different harmonic ranges here. The red one, this one, this one, this one, and this one, that's a harmonic range. So for example, if we think of these 2 points as being the interval, then this one divides this in the ratio of maybe 1 to 6 or something. And this one divides also the same interval in the ratio of 1 to also 6. This one's a little bit further away from this point than this one is. How about the black points? This one, this one, this one, and this one. So if we consider this interval first, this is dividing that interval in the ratio of 1 to 2 roughly, while this is dividing the same interval in the ratio of 1 to 2 roughly, a little bit more. And say the blue points. So again, this thing here, if we consider this as the base interval, this is almost at the midpoint, but not quite, a little bit on this side. So this is in the ratio of maybe 1 to 1.3. And similarly, this is in the ratio of 1 to 1.3. And then there's also these green triangles, 1, 2, 3, 4. So we don't have to always consider this. We could also consider this to be the relevant pair. So if we think of this interval, this thing here divides in the ratio of something to something. That's the same as the ratio this something to that something. So have a look at those different ones and try to get a sense of what a harmonic range looks like. Now you can go back to those diagrams that we drew with poles and polars for our circle, or in fact even for the other conics too that we saw in the geometric sketchpads. And you can visualize any line through the point, through the pole, meeting the conic in 2 points, also meeting the polar line in a third point. Then the 4 points always form a harmonic range. Just go through visually, see what harmonic ranges look like. Here's an important theorem about harmonic ranges. This is the theorem that really asserts that the notion is not really an affine notion. It appears to be, because it appears that we need the scale on the line in order to define the ratios of those various displacements. But that turns out to be a little bit of a red herring. This theorem says that the geometry involved is really projective. What's the theorem? It says the image of a harmonic range under a projection is another harmonic range. What does that mean? Okay, here's a line with 4 points, A, B, C, D, and these 4 points are harmonic range. Here's some point P not on the line. Here is another line. And we're projecting the 4 points on the first line to 4 points on the second line, A prime, B prime, C prime, D prime, by joining everything to the point P, thinking of that as a projection from the point P. And the claim is that these 4 points on this line form a harmonic range too. And of course, we could use any line. It's not just these two. We could choose any line, and it would meet those 4 green lines in a harmonic range. It's a beautiful fact. That previous theorem, the harmonic ranges theorem, suggests that we should introduce a notion for 4 lines, which is analogous to the harmonic range definition for 4 points. And that's what we're going to do now. It's a very useful notion. It's called a harmonic pencil. Pencil is a word that projective geometers use for all the lines going through a particular point. So if we look at all the lines going through the point P, we call that a pencil of lines. Just like if we look at all the points lying on a line, we call that a range of points. So suppose that A, B, C, and D are harmonic range of points on some line, and P is a point not on the line, and we connect those 4 points to P, forming lines K, L, M, and N. Then we'll say that K, L, M, and N are a harmonic pencil. And what we've just seen is that if you have a harmonic pencil, then if you take any other line and see where that any other line meets the harmonic pencil, say that point, that point, that point, that point, that's got to be a harmonic range. That's exactly what the harmonic range theorem that we just mentioned states. So a harmonic pencil gives you automatically lots of harmonic ranges. Okay, so this notion of a harmonic range or a harmonic pencil is very important in projective geometry, very important in hyperbolic geometry too. It appears not just in Apollonius' theorem about poles and polars of conics. Well, that's one very important place where it appears. But this notion also appears in a lot of other places too. And I want to mention some of them to you now, so you get a sense for the richness of this idea of a harmonic range of points or a harmonic pencil of lines. So, the harmonic bisectors theorem. Okay, this is my name for the following fact. That if you have two lines, L and M, meeting at some point, these two lines have what you might call bisectors. This is a Euclidean geometry concept. So where we just look at a line which is equally spaced between the two lines L and M. If you're working with angles, you would say this angle is equal to this angle. So you'd call this an angle bisector. If you were working with rational trigonometry, you would say that this spread is equal to this spread. You'd call this a vertex bisector. And there are always two such. There's that one there, and the perpendicular line is also a vertex bisector. So there are always two lines that bisect any given pair of lines. So if R and S are the bisectors of the vertex formed by the intersecting lines L and M, then L, R, M, and S is a harmonic pencil. It's an easy way of getting harmonic pencils very quickly, just by taking any two lines and forming the two bisectors of them. So in particular, if you choose any other line and look at the 4 points that you get by intersecting with those lines, then you're getting a harmonic range of points. Or to put it another way, so that, for example, these 2 points are going to be harmonic conjugates with respect to these two, and these two are harmonic conjugates with respect to these two. Here's another way of getting harmonic pencils of lines, using just a little bit of vectors in the plane. We'll call this the harmonic vector combinations theorem. I don't mind if theorems have rather long names, if those names are descriptive. I much prefer that to calling something Fred's theorem or Jane's theorem. It's good when the name of a theorem almost suggests what the theorem is about. So this theorem says that if u and v are linearly independent vectors in the plane, say, then the lines spanned by u and v are harmonic conjugates with respect to the lines spanned by u minus v and u plus v. So we're talking about harmonic conjugates now in the context of lines and pencils of lines rather than in terms of points. But I hope the meaning is clear. It means that we have 4 lines which form a harmonic pencil. Okay, here's the picture. We have one vector u right there, another vector v right there. We're going to have all our vectors coming from this base point here. So those 2 vectors, first of all, form 2 lines, the lines through those vectors. And now here are 2 other vectors. The vector u plus v, obtained by taking u and v. So there's the vector u plus v. And the vector u minus v, there's the vector u. Now we're subtracting v. So this is u minus v. So the claim is that u plus v and u minus v form another pair of lines which are harmonic conjugates with respect to the lines through u and v. It's another nice way of easily creating harmonic pencils of lines. So our last example today of a harmonic range of points is the one that's probably most familiar. It's a little bit complicated, but it's very important. You have to really understand, memorize this example. Okay, we'll state it as a theorem, the harmonic quadrangle theorem, which is my name for it, but it's a well-known fact. If PQRS is a quadrangle, so there's 4 points, no 3 of which are collinear, then these 4 points here, A, B, C, D, form a harmonic range. What are these 4 points? Well, A is the meet of PS and QR. So 2 sides meeting at this point. C is the meet of SR and PQ, a meet of 2 other sides of the quadrangle. Those 2 points, A and C, form a line. And on that line we have 2 other points, B and D, which are obtained from the 2 other lines of the quadrangle, namely PR and SQ. So a quadrangle has 6 lines determined by those 4 points. All 6 lines are being involved here. 4 of the lines are being used to find intersections, and the other 2 are being used to find the other auxiliary points. So with this notation, the theorem is saying that B and D are harmonic conjugates with respect to A and C. And from that, of course, we can deduce that A and C are harmonic conjugates with respect to B and D. And we just say that A, B, C, D is a harmonic range. Very important example. So here is a useful exercise. Verify each of the last 4 theorems in special cases. Make some constructions, and then verify that this, for example, is actually a harmonic range. How do you do that? By taking your ruler, marking out the positions of those points, and then computing 2 ratios of displacements. AB over AD, for example, CB over CD. Compute those 2 ratios, show that they're equal to each other, up to a minus sign. So that we get some practical experience for each of these ways that harmonic ranges and harmonic pencils can occur. There are in fact other ways that harmonic ranges and pencils can occur. It's a very rich concept, and it will intersect hyperbolic geometry in lots of ways. Next time we're going to look at another great mathematician from antiquity, Pappus, and the notion of cross ratio which he introduced. Cross ratio very closely connected with the notion of harmonic range of points, but going a little bit further. That'll be crucial for us in hyperbolic geometry. So we're not actually just learning about hyperbolic geometry here, we're also reviewing a lot of very classical and important geometry. And I hope you'll agree that it's all very pleasant. Alright, so that's good. I'm looking forward to the next one. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.